Hello dear students, welcome you all for transmission and distribution class. So continue with the performance of transmission lines. Today we are going to see the long transmission line. In previous classes we have seen short transmission line, medium transmission line. In that we have seen end condenser method, nominal T method, nominal pi method. Now the long transmission line, which is more than 150 km of the length. So here the lumping of capacitance not give the fruitful result for the long transmission line, because the transmission line is having high distances. So that lumping the capacitance at one point will give us the error. So analyzing the long transmission line, rigorous method is used in practice. So the figure you can see here, Vs is sending end voltage I plus Di, where V plus Dv is the voltage we are going to take, and the impedance is Z into Dx is there, and capacitance Y dx is there, and the receiving end side current I V is there, Vr is the receiving end voltage. You can see that here, considering the small element of the line of the length dx is situated at a distance x from the receiving end. You can see the things clearly. The small length dx is situated at a distance of x from the receiving end. Okay, now we will see Z is the series impedance of the line per unit length, Y is the shunt admittance of the line per unit length, V is the voltage at the end of the element towards the receiving end, V plus dV is the voltage at the end of the element towards sending end, I is the current at the leaving element dx, means current leaving at element dx, I plus Di is the current entering to the element dx. For the small element dx, Z dx is the series impedance and Y dx is the shunt admittance. According to Ohm's law, we can write that dV is equal to Iz dx, where dV by dx is equal to Iz. So current through the shunt admittance is given by Di is equal to Vy dx, or Di by dx is equal to Vy. These two equations we need to take. One is dV by dx is Iz, and Di by dx is Vy. So differentiating the equation 1 with respect to x, we will get d square V by dx square, that is Z di by dx here, or di by dx is nothing but Vy. We will write that d square d by dx square of V is nothing but Z Vy, Z dVy. Okay, that is equation 3. So the solution of this differential equations can be written by, we are knowing solution of these equations. So that is V is given by k1 into cos hyperbolic of x into square root of yz plus k2 into sin hyperbolic of x into square root of yz. This is the differential equation solution. We are knowing the how to solve the differential equations. You have studied it in mathematics. Okay. So now differentiating the equation 4, we will get dV by dx is equal to k1 into square root of yz sin hyperbolic of x into yz plus k2 into square root of yz into x into square root of yz. Or we know that dV by dx is Iz. So in the place of dV by dx, we will put that as Iz, where that is k1 into square root of yz multiplied by sin hyperbolic of x into square root of yz plus k2 into square root of yz into cos hyperbolic of x into square root of yz. So we take the z to the RHS side. So anyhow that square root of yz is there. If you are dividing it by z, your one part of z at the numerator is getting vanished with the square root of z. The remaining part of the square root of z is at the denominator. Okay, y by z. That actually square root of z get cancels. The another part of square root of z comes at the denominator side. So this is what the equation 5 shows after the cancelling the square root of z one part. So that is square root of y by z is taken as common now. The value of k1 and k2 can be found by applying the end conditions as under. At x is equal to 0, that is the at the end point. You can see at x is equal to 0, v is equal to vr, no, and I is equal to ir. So putting the values, we will get Vr is equal to k1 of cos hyperbolic of 0 plus k2 of sin hyperbolic of 0. We know that cos hyperbolic of 0 is 1 and sin hyperbolic 0 is 0. So Vr is equal to k1, or directly we can write it as k1 is same as Vr. Similarly, we will put the x is equal to 0, v is equal to Vr, and I is equal to IR in the equation 5. So IR is equal to, in the equation 5 we will get like this, or so same thing here, sin hyperbolic of 0, cos hyperbolic of 0 will come. Now here k1 will become 0 because of sin hyperbolic 0 is 0, k2 into cos hyperbolic of 0, cos hyperbolic 0 is 1, and k2 as it is. So we will get k2 is equal to square root of z by y into IR. Substituting the k1 and k2 in equation 4 and 5, we will get v is equal to VR cos hyperbolic of x into square root of yz plus square root of z by y into IR sin hyperbolic of x into square root yz. Same thing, I is equal to square root of 5 by z VR sin hyperbolic of x into yz plus IR into cos hyperbolic of x into square root of yz. So this is what the two equations we are getting. So so sending end current and voltage are obtained by putting the value of x as L in the above equation, because total length is L if you are considering. Where the x is there, we will put that value as L. So we can write in then when x tends to L, or V becomes Vs, and I become Is. So we can write Vs is equal to VR cos hyperbolic of L into square root of Iz, that x becomes L now, plus square root of z by y into IR sin hyperbolic of L into square root of Iz. Same thing for the equations I, that is I is nothing but Is, square root of Iz VR into sin hyperbolic of L into square root of Yz plus IR cos hyperbolic of L into square root of Yz. So now we will write L into square root of Yz, or taking the L inside the square root, it will become L square. If it is L square means we are having two L's. So one L is multiplied with small y, and one L is multiplied with small z. So total actually y and z are the per unit value. If you multiply it by means per kilometer length, multiplied by length means it will become a total value. That's why it is capital Y and capital Z. Same thing here for the L into YZ. Here that L will come inside. So here also L is multiplied by Y, L is multiplied by Z, because if L comes inside means that will become L square. Okay, L square in bit will come inside. So L by Y we are taking, that is Ly by L by Z, that is Y over Z. So Y is the total shunt admittance of the line, Z is the total transmission impedance of the line. So we are writing Vs is equal to VR cos hyperbolic of square root of Yz plus IR into square root of Z by Y into sin hyperbolic of square root Yz. Same thing, Ys is equal to VR cos VR into square root of Y by Z into sin hyperbolic of square root Yz plus IR cos hyperbolic of Yz. So this is the, if you want the expansion of the hyperbolic sign, we will have cos hyperbolic of square root of Yz is equal to 1 plus zy by 2 plus z square y square by 24, like that it is moves. Same thing for sin hyperbolic of Yz. This is the series expansion of the hyperbolic functions. Okay, this is regarding the long transmission line. So you try to write down these equations by your own, because you need to write the derivation for the long transmission line. Usually this is called as the rigorous method. In the examination you will get the question in terms of write the long transmission line performance using the rigorous method. Then you need to draw this figure and you have to explain the things of derivation. Okay, so this is the long transmission line. In the coming classes we will see some problems as well as the ABCD parameters. So you have seen the different methods now. Short transmission line method, you have seen the condenser method, nominal T, nominal phi, and rigorous method. All these things we can express using the ABCD parameters. Okay, so finding the sending end voltage and sending end current using the ABCD parameters in different methods. You see it in next class. Okay, if you find any difficulties you can ask. Thank you.